this video, I'm going to look at one-dimensional SUVAT equations. In a subsequent video, I'll look at how you apply them to two-dimensional problems, but that comes after we can apply them to one-dimensional. I'd also recommend you watch my mechanics video on general skills, because some of the content I use in here has been explained in more depth in that video, so I would do that first. Anyway, let's crack on. So first of all, when can you apply SUVAT equations? They're designed to be used as a model for the motion of an object, and they can only be used when the acceleration on an object is constant. Otherwise, they don't give an accurate approximation. This is one of the main reasons air resistance is always ignored when doing problems like this, because if you have air resistance, it's a very complicated force, and you wouldn't be able to assume that acceleration was constant. The other thing you need to know is the notation that is being used in the equations. So we've got v, which is your final speed here. We've got u, which is your initial speed. S is your change in displacement. A is your acceleration, and t is the change in time. So that's the notation that will be used in subsequent slides to make them more brief. Okay, so let's derive the SUVAT equations. There are four key equations you need to know. There is technically a fifth, and I'll show you what it is, but that's not one you'd be using very often, or if at all. Anyway, so let's start from basic principles. The final velocity of an object is the initial velocity plus a change in velocity. Hopefully that makes sense to you. So you've got an initial velocity, we increased it by a certain amount, and that gives you your final velocity, or v equals u plus delta v. As I talked about in the general skills video, acceleration is the change in velocity over the change in time in which that change occurs. And we defined t in our notation as change in time, so that's why it's not a delta t there. So if we rearrange this, we get delta v is at. And if we substitute that back into this original equation, we get v equals u plus at, which is the first SUVAT equation. We're going to need another equation, and then we're going to use that to derive the third and fourth, but let's get that second equation. So you should also know that the average speed of an object is the change in displacement over the change in time at which that occurs. Or in other words, the v average is s over t. We also know the average speed, because acceleration is constant, is the initial speed plus the final speed divided by 2. That's how you calculate an average of anything. So we put those two things together. We can rearrange them into this form, and this is the form you see the second SUVAT equation in most often. S equals u plus v over 2 times t, and that's your second SUVAT equation. So if we look at here, we can do some calculations without using a in here. If we look at this one here, we can do calculations without using s. But what if we don't know v or we don't know t? That's why we need a third and fourth SUVAT equation, and we get those by using the first two SUVAT equations. So this is substitute 1, which is v equals u plus at, into 2. So we're essentially, you see where this u plus at, we've substituted in for v. If we collect the terms, we get this expression here, and then if we do some cancelling out, we end up with s equals ut plus half at squared, and that's your third SUVAT equation, and you'll notice it doesn't include v at any point. You don't need to know the final speed. To get the fourth SUVAT equation, you need to rearrange the first equation into this form here to get t by itself. Once you've got that, you can substitute it in. So we've substituted it in for t here, and take the 2 and the a over to this side, multiply out brackets and rearrange, and you get v squared equals u squared plus 2as, the fourth and final SUVAT equation. Now I mentioned earlier there's actually a fifth one that we don't really need to know. And that more eagle-eyed of you has spotted, well, what if we don't know u? Very good question. What if we don't know u? Well, let's rearrange the first equation into a form where u is the subject. So we get this, substitute it in, so we put it in for u here. Then collect the terms and generate this fifth SUVAT equation, which you'll notice is very similar to the third equation, but with v instead of u. And you'll also notice for some reason there's a 3 there, should say 5. Don't know what's going on there. Anyway, And the reason we never use this is because these equations are designed to model what will happen to an object. So u is almost always a known quantity, and if it's not, it's usually calculable from equation 1. So that's the reason we never use this equation, because it's not telling us anything particularly useful, but it's there just in case you were wondering why we're not using it. Okay, so let's have a look at some examples of putting these into practice. Okay, so we've got a car travelling at 20 meters per second. The accelerator is designed to cause the car to accelerate uniformly at 2 meters per second squared, and calculate the final speed after 10 seconds. So first of all, can we apply SUVAT? Yes, we can, because the acceleration is uniform or constant. So the thing I get my students to do here is write out the parts of your SUVAT, and let's see if we know them. So that's our unknown that we want to calculate. This is 20, this is 2, this is 10, this we don't know. Because we don't know displacement, we need to use the first equation. So v equals u plus at. Let's put some values in. So we've got 20 plus 2 times 10, which gives you 40 meters per second. Okay, nice and simple. That's neatly typed out if you can't read my handwriting, but obviously we get the same answer. Okay, so that's a very simple one. Let's have a look at some slightly more complicated examples, but they're not much. So again, we've got a car travelling at 20 meters per second, again accelerating uniformly at 2 meters per second, so we can apply SUVAT. This time it wants you to calculate the distance covered in 10 seconds. So let's do this. So this is our unknown. This one is 10. Again, we know that's 2, 20, and we don't know v. So we need an expression that doesn't have v in it, which means we need equation 3, which is this one here. Half 80 squared. Let's put in our terms 20 times 10. If you see dots in my presentations, it's just shorthand for multiply. It's nothing more complicated than that. 10 squared. And then let's do the calculation. So we get 200 plus, that's 100 times 2 is 200, divided by 2, 100, gives you 300 meters. Okay, so that's that one. And there it is again typed out in case you can't read my handwriting. That's that one. And let's look at one final example. So again, travelling at 20 meters per second. Again, uniform acceleration 2 meters per second squared. This time it wants to know the final speed if the acceleration occurs over 100 meters. So this is what we want to know. This again 20, this again is 2. T we don't know this time, this is a 100. That means we're going to need equation 4 because it doesn't have t in it. 2as, and obviously we want to calculate v, so let's square root the whole thing. You'll notice in these that I always arrange algebraically before subbing numbers in. That's very good practice, something you'll especially be encouraged to do in science type subjects. It's not so much of an emphasis in maths, but I will always do it like that. So square root of 20 squared plus 2.2 times 100 was square root of, so that's 400 plus 400, so square root of 800, which should come out at 20. That looks a bit messy. 28.3. This is velocity, so it's meters per second. Now we're given it to 3 significant figures. Always a safe number to give as an answer to a question. And once we've got the full written out typed explanation. So that's the end of applying things to one-dimensional problems, and the next video I'll show you how to apply them to two-dimensional problems using either IJK notation, column vectors, or angles.